Hi everybody, I hope this video finds you well. In today's video, we're going to finish up our investigation of regression and modeling using the LSR, making predictions, all the stuff that we've sort of been building up to. We're sort of going to wrap up that piece of our course by discussing a little bit of a concept called residual analysis, which is basically a way of helping us understand if the linear model, the one that we've sort of learned how to build in our class, is the right choice or if it's the appropriate model for our data. Now, again, since our course is a survey course, the only model we're learning how to build is a linear model. But obviously, as we discussed at the very beginning of correlation and scatter plots and things, there can be many other forms such as exponential and nonlinear that if you took further statistics courses, you would learn how to build models for those patterns of data as well. So the question in this video is, if we choose a linear model, how do we know if it's the right choice or not? So to analyze that, we have something called residual analysis. So the main question is, how do we know if choosing a linear model is the actual right choice? So to study this, we build something called the residual plot. Now, of course, the residual plot is going to be based on residuals, and just remember as a quick note, residuals, as we saw in the previous video, they're defined as taking the actual response and subtracting the predicted response. And remember, you can do that for any data point in your sample. So what is a residual plot? Well, a residual plot is a scatter plot where we keep the explanatory variable on the horizontal axis, just like normal, but we put the residuals on the vertical axis. So in other words, instead of having the response variable on the vertical axis, in a residual plot, you're plotting the explanatory variable versus the residuals. So what are we looking for when we build one of these residual plots? Well, a quote-unquote good residual plot will look random and scattered, meaning that those residuals, those errors, they should be random and scattered. There's always going to be errors, right? No model is going to be perfect, but we want those errors to look random and scattered. This, if we see that, indicates that our choice of a linear model is appropriate. In other words, this really confirms that the form is linear, and choosing a linear model is appropriate. A quote-unquote bad residual plot is going to show a clear pattern. Usually that pattern is going to be like a U-shape or an upside-down U-shape. This indicates that our choice of a linear model is not appropriate. In other words, if you see a pattern to the errors, this indicates that the errors aren't just coming from only being able to estimate what's going on. This means that there's something sort of fundamental, something that we sort of missed in the data because the errors are showing a particular pattern. The thing that most likely is causing that pattern is that there's actually a different form for the pattern rather than linear. So for us, if we see a pattern to the residual plot, either a U-shape or an upside down U-shape, then this actually indicates that we shouldn't have chosen a linear model. The appropriate model would have been exponential. Now again, in our class, we're not going to learn how to build that exponential model, but we just want to be aware that if we choose a linear model, that it doesn't guarantee that it's the right choice. So if we see this U-shape or this upside down U-shape in our residual plot, we know that, well, we chose the wrong type of model for the data, and that's as much as we can say for this course. So let's talk a little bit more about exactly what these good and bad residual plots might look like. So here are some examples. You'll notice a couple things about residual plots. Notice that the explanatory variable in each is on the horizontal axis, and you'll know that notice that the residuals are now on the vertical axis. Also, you'll notice that I'm floating 0 up in sort of the middle here. This is something we're going to standardly do when we build a residual plot, because remember, some residuals are going to be positive and some are going to be negative. So instead of having sort of a piece down here and putting negatives up down there and positives up here, we like to keep it all in one quadrant. So we'll put 0 sort of in the middle, negatives will be down here, positives will be there, and it just makes it sort of look like a more normal scatter plot, but allows us to have both those positive and negative values. So in a residual plot like this, there's our explanatory variable, there's our residuals. You'll notice that the residuals are all over the place. This is what we sort of mean by a good residual plot. So this would be considered good, and this would imply that our choice of a linear model is appropriate. Now again, that doesn't say that the relationship is stronger or weaker or whatever. It's just saying that the choice of building a linear model, of trying to fit a line to the data, is a good choice. Doesn't necessarily mean that that line fits super well or not that well or whatever. It just means that choosing a line is the appropriate form for the pattern. If you see something like this, you'll notice that there's a strong sort of pattern. The residuals seem to go like that. It's like an upside down U shape. In this case, we would consider this sort of bad. And what this actually means is that the linear model is not appropriate. And what that, again, means, especially when we see this actual, like, upside down U shape, or if we were to see something that sort of makes a U shape, it actually means, we'll just put a note here, actually data is exponential. And if you think back to the very beginning of when we started our correlation and regression thinking and our investigation, we talked about how linear and exponential were similar forms because they both were monotonic. The linears are either positive or negative, and same thing with exponentials. So you can see why if we're looking at a scatter plot, it might be hard visually to know if something is truly linear or if it's exponential. So this residual plot sort of helps us make that determination. Again, for our class, the only type of model we're going to learn how to build is the linear one, and we've already seen how to do that through the LSR, but we just want to be aware there are other forms out there, and we want to be able to diagnose if our form is really the appropriate one. So there we go. That's what these sort of residual plots are going to look like. Let's get to an example where we'll actually be able to build one of these residual plots and sort of make this diagnosis of whether or not a linear model is appropriate or not. So let's go ahead and take a look at our example here. So for this example, we'll zoom out just a little bit so we can get a better view there. So for this example, we're going to suppose that we have a researcher that's studying the relationship between the mileage and the resale value for a particular type of vehicle. In this type, we're looking at Nissan Rogues, which are like an SUV produced by Nissan. So to do this, the researcher randomly selects 9 Nissan Rogues and gets the following data. So they had different mileages. So one of them only had 15,000 miles on it. Notice that the mileage is in thousands of miles. So one of them had 15,000 miles, one had like 75,000 miles, one of them had all the way up to 120,000 miles. So obviously this one had not been driven that much. This one had been driven a good amount. This one had been driven quite a lot. And then we have their resale value, so basically how much they're valued at in dollars. So you'll notice that the one that had only been driven 15,000 miles was valued at like $20,000 and $200, whereas the one that had been driven 120,000 miles was only valued at $2,700. So in this example, we're going to run through pretty much everything we've talked about with correlation and regression. Notice that we're going to draw the scatter plot, so we'll get one more chance to sort of visualize this. We'll calculate the correlation coefficient and use that to determine if there really is a relationship between mileage and resale value. We'll construct the LSR, so we'll figure out the equation of the linear model. We'll draw that linear model on the scatter plot and really, again, confirm, I mean, even though we've done it several times, but we'll confirm that that LSR really does fit the general pattern of the data. We'll talk about what the slope and intercept, the two components of the LSR, mean in this context. We'll use the LSR to predict the value of a Nissan Rogue with 60,000 miles, and we'll talk a little bit about whether or not we would trust this prediction. We'll calculate and interpret the coefficient of determination, which remember was a measure of predictive power, and then we'll construct a residual plot for this data, and we'll actually try to determine is the choice of a linear model appropriate. So a bunch of things to do, but if we can go through and do this, then we're pretty much comfortable with everything we've discussed for correlation and regression. So to start off with, let's go ahead and grab this data, and we'll try to do almost everything on sort of a separate page here. So let's go ahead and copy that. Okay, so let's give ourselves sort of a fresh page here. We'll go ahead and paste our data in right there. Okay, so let's go ahead and start with A, which is supposed to be our scatter plot. We want to visualize this. So which of these variables should be viewed as explanatory and which is response? Well, hopefully we should be convinced that the mileage, right, the amount of miles that the car is put on or that people have driven it, should probably impact the resale value, not the other way around. So this will be our explanatory, and when we get to the calculator part, we'll be putting that into L1, and the resale value will be our response, which we'll eventually put into L2. Let's go ahead and draw our scatter plot. So we'll give ourselves an axis there. Remember that this here will be our mileage, and that's in thousands of miles. And this over here will be the resale value, and that's in dollars. Okay. So let's go ahead and get some axes here. So for mileage, it looks like we're as low as 15 and goes all the way up to 120. So we could maybe start actually at 0 and just go by 20s. Nice and easy. 20, 40, 60, 80, 100, and 120. And notice that by doing that, we don't need any condensing of the axis there. We'll just start at 0 and go by 20,000 at a time. Then there's our horizontal axis. For the resale value, it looks like the resale value is as low as 2,700 and as high as 20,000. So again, we could just go ahead, maybe we'll just go by 2,000s, 2, 4, 6, 8, 10, 12, 14, 16, we'll extend our axis just a little bit, 18, and 20. So there's 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14,000, 16,000, 18,000, and 20,000. You know, that's a little bit messy, so let's just we'll just sort of choose a slightly different axis, maybe make it a little easier on ourselves. A little messy there, I apologize. So let's go ahead and we'll just get rid of that. I'll just redraw. You know, let's maybe just go by like 4,000s or something, make it a little bit easier. So 4,000, 8,000, 12,000, 16,000, 20,000, and technically we have to go a little beyond 20,000, so there we go. So there's 4,000, 8,000, 12,000, 16,000, 20,000, and 24,000. Okay, so there we go. Again, no need to sort of condense anything because my scale is 4,000 at a time for each axis piece. All right, let's go ahead and plot these points. So the first one we had was 15,000 miles and a resale value of 20,200. So that should put us right about there, I would say. Okay, and then we had 30,000 and 30,000 miles and 16,000 as the resale value. So there we go. Then we also had another 30 with 14,600. So that looks like it should probably be right about there. Then we had 45 and 11,400. So that looks like it should probably be right about there. Then we had 50 and 10,300. So probably somewhere right about there. Then we had 75 and 6,400. So it looks to be maybe right about there. And then 105 and 3,600. So maybe right about there. And then 120 and 2,700. So probably right about there. So there we go. There's our scatter plot for this, and certainly we can see that this is negatively directed. As the mileage goes up, we see the resale value going down, which should make sense, right? The more mileage a vehicle has, the less value it's going to have. Okay, so let's go ahead then and get that correlation coefficient. So we'll go ahead and do this part B here. So we need to get the correlation coefficient, so now it's time to go ahead and put that data into our calculator. So if you have anything in L1 or L2, you can clear that out. Then go ahead and put those mileages in. Keep in mind, the units are in thousands of miles, so you can just type in 15, 30, 30, 45, etc. We'll make sure that when we write out any interpretations, we always say thousands of miles, but you don't have to type 15,000. You can just type 15, 30, 30, 45, because the units have handled that for you. So we'll put in 15, 30, 30, 45, 50, 75, 85, 105, and 120. And then in L2, we got to put those values. 20,200, then 16,000, then 14,600, 11,400, 10,300, 6,400, 5,300, 3,600, and 2,700. And once we go ahead and do that, if we do our stat calc that linreg ax plus b. Let's go ahead and get our r. Looks like our r value here is going to be about negative 9.650. Notice we do get a negative value there, which makes sense because we just visually we should know that this is negatively directed. We should probably already be convinced that there's enough evidence here because this is pretty close to -1, but technically to confirm that, we do need to go ahead use that table E. In this case, we had 9 data points, so let's go ahead and do that. So I believe we have table E right here. Yep. So there we go, 9 data points. We're going to intersect that with this here, and it looks like our critical value that we need to get over is 0.6664. So our critical value here is going to be 0.6664. This in absolute value, 0.9650, is definitely going to be larger than this. So we can say the absolute value of R is greater than the critical value, which implies that there is enough evidence for a negative correlation. So in other words, we are convinced that there's a negative relationship, that as the mileage goes higher, the resale value is going down. And it's a pretty strong one because, of course, this is pretty close to -1 and is certainly strong enough based on the amount of data because it made it over that critical value. All right, let's go ahead and get the equation of the LSR. So what does that LSR actually look like? Well, if we grab the A and B, we should find, we'll just round everything to whole numbers because it's pretty large here. We should find negative 160x, so the A was negative 160, plus 19,942 for the B here. So there we go. So negative 160x plus 19,942. And again, if you prefer, you can always write that out as that the sort of predicted value is negative 160 times the mileage plus 19,942. All right, we also, I believe for part C, we constructed the LSR, but we also wanted to draw it. So let's remind ourselves how to do that. Remember, we need to choose 2 explanatory values. So I'll do that in blue here. So to draw LSR, we need to choose 2 explanatory values. So we could say, let x equal 0. Why am I choosing x equals 0? Because that's where I started my axis, so I might as well just do that to make it nice and easy. Plus, plugging in 0 is always nice and easy. So the predicted y will be negative 160 times 0 plus 19942, which is going to give me 19942. So my first point is x is 0 and y is 19,942. Putting that on our graph, we should have something basically right there, right under that 20,000. And then our other one, let's go ahead and let x equal, we can do the 120 as well. So let's do the 120. And if we do that, we should get that the predicted y is negative 160 times 120 plus 19,942. And if we type that into our calculator, we should get 742. So if we plot that on here, it should be very, very small somewhere down here. So if we draw our connecting line, it looks like our connecting line should look something like that. So there we go. Notice it does sort of generally seem to fit the data, right? Some points are above it, some points are below it. So again, really that LSR that the calculator is generating for us really does fit the overall pattern of the data. All right, let's go ahead and talk about some of the components of that LSR. So let's talk about that slope and the intercept. So we'll talk about the slope first. The slope, of course, is that negative 160. So remember, algebraically, we know that the slope means that when we go up 1 in x, this slope is what happens to y. So we would go down 160 in y. What does it mean to go up 1 in x? Well, x was the explanatory, which was the mileage. So when we go up 1 in the mileage, we're going down 160 in the value. When we go to write our interpretation, make sure to include the units. How did we measure the mileage? Well, it wasn't in miles, so this isn't 1 mile. This is actually going to be 1,000 miles because we measured the miles in thousands, and the value was measured in dollars. So we'd say for each additional 1,000 miles, a Nissan Rogue has, its resale value drops by $160. So in other words, we're saying that for every additional 1,000 miles that the Nissan Rogue has on it, right, then that resale value drops by 160. If we accidentally forgot about the 1,000 and we said for each additional mile the Nissan Rogue has, its resale value drops by 160, just notice by common sense we would realize that that makes no sense, right? Because we're saying basically every time you drive this vehicle 1 mile, its value drops by $100 some. That doesn't make any sense. But driving it 1,000 some miles, which is a good amount of use, yep, the resale value should sort of drop from there. Let's talk about the intercept. Since we're asked to interpret it, it must make sense here. So what was the intercept? It was the other value. That was that 19,942. So remember, the intercept is when x is equal to 0, y is equal to this intercept value. So x being 0 means that the mileage equals 0, and the value would be 19,942. So what does it mean for the mileage to be 0? You might say that doesn't seem to make sense, but keep in mind, mileage being 0, that would probably indicate a brand new car. So this is saying that a brand new one of these Nissan Rogues, according to our model, if they have 0 miles, should be valued at $19,942. So we'd say a brand new Nissan Rogue, i.e. with no mileage, is valued at $19,942. And notice that that should sort of make sense, right? This is sort of saying that these vehicles start off at about $19,942, a little under $20,000, and then for every 1,000 miles that they sort of have put on them, their value drops lower and lower, right? So the more and more the vehicle has been used, the less and less valuable it's going to be. So there we go. We interpreted the two components to the LSR, the slope and the intercept. Let's go ahead and see what else we need to do in building up to ultimately building that residual plot and trying to determine, is this really an appropriate choice, this linear model? So we want to predict the value of a Nissan Rogue with 60,000 miles. So let's see how we can do that here. So we've got this Nissan Rogue with 60,000 miles. Okay, so as we know, whenever we need to predict something, that means we're going to plug into our LSR. Now, if we look at our equation here, it might be tempting to just immediately throw in the 60,000, but we have to be very careful. In terms of the 60,000 miles, notice that we need to view that as x equals 60,000, because remember, the units for our explanatory is thousands. So we're not going to plug in 60,000, we're going to plug in 60, because our variable is in thousands. Notice then that the predicted value is going to be negative 160 times that 60 plus 19,942. We can go ahead and calculate that. Negative 160 times 60 plus 19,942. You should get that this predicted y is about 10,342. So our model predicts a Nissan Rogue with 60,000 miles should be valued at $10,342. And you can see why this would be useful to make a prediction like that. Maybe you're trying to buy one of these, you find one that's got 60,000 miles on it, and maybe it's listed at $12,000. Well, according to our model, you would be overpaying because it should only be worth $10,342. Maybe you find another one that's listed at $9,000. Oh, that would be a great deal if it had 60,000 miles, because according to our model, it's worth about $10,342. So again, you could use this to make a decision about whether or not purchasing one of these, given a certain amount of mileage, would actually be a good choice. Now, we always have a follow-up now. Could we trust this prediction? Well, we need to think, is this 60,000 miles in the explanatory range? Well, we can go back and look. Notice that we had vehicles that ranged from 15,000 to 120,000 miles. So certainly 60,000 miles is in the range. So we can say we can trust this since 60,000 miles is in the explanatory range, which was 15,000 to 120,000. So we'd be comfortable using this model probably for like brand new Nissan Rogues, ones that have like 10,000 miles, 30,000, 50,000, 60,000, 80, 90, 100, maybe 130,000, but we wouldn't probably be comfortable using this model to predict like the value of a Nissan Rogue with 200,000 miles, because our data was from 15,000 to 120,000. All right. Let's go ahead. I think we've got one more part before we get to the residual plot. We want to calculate and interpret the coefficient of determination. So we'll do that right here. So coefficient of determination, that's the r squared. If you still have your data typed in, you can go ahead and do calc ln reg ax plus b and just record the r squared, or you could just literally square the r value. Either way, you should get r squared is about 0.9313. We want to interpret that. Remember, we always interpret the coefficient of determination the same way. We would say 93.13% of variation in the response. Remember, the response here is resale value. So 93.13% of variation in resale value can be explained by changes in whatever the explanatory is. So in this case, in mileage. So, in other words, the sort of mileage accounts for about like 93% of the variation that we're seeing in the resale value. The other 7% of variation, well, it must be due to other factors, which makes sense, right? Mileage is not the only thing that determines the value of a vehicle, but it is, of course, an important component, and we're saying that in this case, mileage is a great predictor for the resale value of a vehicle. All right. At this point, this was all review of what we've been covering in the previous few lecture videos. Now let's go ahead and take this one step further and actually determine if the linear model is an appropriate choice, right? That's the one we built. We just did some things using it, made some predictions with it, but is it really the correct choice? So let's give ourselves one more page. We still want to bring this data along with us. So I'll take that. No, I think we actually still have it saved, so let's go ahead and just... Yep, there's our data. Okay. All right, so this is going to be, I guess, what is that? Part G at this part? Okay. So just remember, right, this is our explanatory and this is our response. To build a residual plot, you need to calculate the residuals. So these are the actual responses. We're going to need to create another column for the predicted responses. So I'm going to do that here. And we'll give ourselves some extra lines there. So I'm going to have to come up with a predicted value for each of these vehicles. And then we're going to have to get the residual, which remember is the response minus the predicted. So we're going to have to basically add 2 additional columns to our table. So we have to add 2 additional columns. All right, so let's go ahead and do that. All right, so there's the explanatory, there's the response. We need to get the predicted responses and we need to get the residuals. How do we get these predicted responses? Well, remember, the predicted response is based on our LSR, which is minus 160x plus 1994, 2. So there we go. Yep, there we go. So what we're going to do is we're going to take each of these explanatory values, plug them in for x, calculate the predicted response, fill those in here, and then calculate the residuals here. So let's do this one at a time. First, we'll have to plug in the 15. So if you're following along with your calculator, negative 160 times 15 plus 19942. So our first one here, just zoom in a little bit, should be 17,542. I'm going to actually go ahead and fill in this column first, and then we'll move to this one. So for this, we'll now plug in the 30 into x. So negative 160 times 30 plus 19942. That should give us 15,142. Okay, you notice that the next one will also be plugging in 30, so it's going to come out the same. So the predicted value is the same. Next one is going to be plugging in 45, so negative 160 times 45 plus 19942, which should give us 12,742. Then we'll plug in the 50, so negative 160 times 50 plus 19942, which should give us 11,942. Then we plug in the 75, so negative 160 times 75 plus 19942. That should give us 7,942. Then we have 85, so negative 160 times 85 plus 19942. And that looks like we should get 6,342. Then we've got 105, so negative 160 times 105 plus 19942, which is 3,142. And then we've got 120. We'll plug that in. Negative 160 times 120 plus 19942, and we should get 742. So those are all the predicted values. So we're saying for each of the vehicles that we saw in our sample, this is how much we thought it should have been worth. Now we can calculate the residuals by simply subtracting across. So we'll take this minus this, so 20,200 minus 17,542. So our first residual should be 2658. Next one, 16,000 minus 15,142, should get 858. Then 14,600 minus 15,142. Notice we'll get a negative. Remember, some of the residuals should be negative, some should be positive. We should always have a mixture. Then 11,400 minus 12,742. So negative 1,342. Next one, 10,300 minus 11,942. Looks like we should get minus 1,642. Then 6,400 minus 7,942 minus 1,542. 5,300 minus 63,000 or 6,342 minus 1,042. Then 3,600 minus 3,142. 458, and then finally 2,700 minus 742. We should get 1,958. Okay, now we are ready to actually draw our residual plot. Remember, the residual plot is going to be the explanatory and these residuals. So let's go ahead and zoom out just a little bit. There we go. So this will be the residual here. Remember, we're going to float the 0 in the middle. Notice that the residuals go as high as like 2,600 and as low as like negative 1,642. So we can just go by 1,000. You can be pretty rough with the residual plot because, again, unless it has a very strong pattern, we're going to consider it appropriate. On this side, we'll have negative 1,000, negative 2,000, and negative 3,000. And then I recommend putting a little dotted line so you can visualize which were positive and which were negative. And this will be our mileage in thousands down here, which I think we can just keep the same. I believe we went by like 20, so 20, 40, 60, 80, 100, and 120. Okay, so our first one was an explanatory of 15 with a residual of 2658. So that should end up being somewhere way up there. Then we had one with 30,000 miles and a residual of 858. So 30,000 miles, 858 should be right about there. Then another one with 30,000 miles and a residual of negative 500. So that should be right about there. Then 45 and negative 1342. So that looks like it should be maybe right about there. Then 50 and negative 1642. So that looks like it should be right about there. Then 75 and negative 1542. So right about there. Then 85 and negative 1042. Okay. Then 105 and 458. So maybe right about there. And then finally 120 and 1958. So 120 and 1958, right about there. So what do we see here? Well, in general, when analyzing residual plots, you want to give things the benefit of the doubt. If it looks like there's some sort of weak pattern, we're going to still just say that the linear model is appropriate. But in this case, there can be no doubt. This is such a clear U-shaped pattern here that we would say that this is what we consider a bad residual plot. And what that indicates is that a linear model is not appropriate. So in other words, choosing to try to model this or fit a line to the data is not the correct choice. Now, let's go back and take a look at our scatter plot and see if this sort of makes sense, that's saying that a linear model is not really appropriate. Well, if we go back and we just take a quick look, notice that should be pretty clear. If we really look at this scatter plot, we sort of zoom in here, what are we really seeing? Is this really forming a line? Well, no, it seems like the line is sort of steeper here and then more shallow here. In other words, we're sort of describing something that probably would have been better served with a curve. It's more exponential in nature. Certainly it is negatively directed, but it seems like it's very steep at the beginning and then more and more shallow as we move forward. So this should have been modeled with an exponential function. Now, if you take another statistics course at some point, you can learn how to build exponential models. It's similar to how we build linear ones, and then that would be the appropriate choice there. If we built an exponential model for this data set and we looked at its residual plot would be random and scattered, indicating it is the appropriate choice of model. So in this case, though, for our class, the best we can say is that the linear model doesn't quite fit, and that's all we can really say. This sort of wraps up our investigation of correlation and regression. We've got a couple more sort of side topics to mention about correlation in general. We mentioned at the very beginning about correlation and extreme values, so we need to analyze that. And we're also going to talk about one further application of correlation, which regards to sort of measuring agreement between individuals. However, in terms of actually modeling and understanding the relationship between quantitative variables, this really sort of wraps that up, because at this point we understood how to determine if there is a relationship, how to model that relationship, and then how to decide if our choice of model is really the correct one.